welcome everybody this evening. Great turnout, and I'm really glad that our speaker has made it here. And please give her a bit of sympathy, because she's not really 100% and her voice might give up. Hopefully not before the end of her talk. Elsa's here to receive the T.N. George Medal. We'll hear more about that. Before we start with that, a couple of kind of notices which you may have seen when you got your newsletter, but I just want to sort of add to them. One of them is that we're interested to hear from any member who might want to think about helping our treasurer. You may be a future treasurer, but you don't need to be a trained accountant, but you only need to help. You don't need to become on council. But if anybody can think of being numerate is a help. But apart from that, anybody's welcome to join us. And the other notice that you'll have had is that the library in the Malema building, which used to be the Gregory building, the Malema building is open on Tuesday the 17th, that's next Tuesday, from 12 o'clock to 3 o'clock. And anybody who likes to come along can pick up as many books as they like. We're trying to move, the library has to be moved out of there. A lot of books have been selected to move into the university library, but there's an awful lot that aren't. And if anybody would like to come and rummage around and take as much as you like, you're very welcome. So that's as far as I go. Now I'm going to introduce Campbell Forrest, who is Vice President of the Society, and he's going to talk about the T. Neville George Medal and give the citation.
It's lovely to see, as Margaret says, lovely to see how many people are here this evening from far away as well, from the island of Ling and Fort William on a free bus. Welcome, Noel. As Margaret says, I've got two things to do this evening. You're just going to have to bear with my voice for just a few minutes here. The second thing I have to do, most important thing, is to just read to you, in you come, Walter, read to you the citation, which is printed in the scroll, which Margaret will present to Elsa later on. And the first thing is just to explain a little bit of the background of the T.N. George Medal. It's a number of years since it's been given. I'm just going to do this slightly differently. Can everybody hear me okay, by the way? So who was Neville George and what was he like? Can I ask if anybody in here was given a lecture by T.N. George? Anybody put their hands up? One, Helen, okay. So there's two of us. And I thought that helps maybe just to make it a little bit more personal. The proceedings of the Society for 1980 give actually a marvellous obituary of Neville George, pages long, and I'm not going to dip into that at all, but I thoroughly recommend you can Google it, bring up the proceedings and read about him. He was a tremendous guy, a real educator. I think it was one of the days before the prime objective, I think, of academics now seems to be to do research, but then it was to educate, and he was an educator in the broadest sense. He was appointed to the chair of geology at Swansea at the age of just 29, and he came up to Glasgow in 1947 and stayed until he retired, and he in fact died in Glasgow in 1980. But what was he actually like? Well, the second lecture that I attended as a raw, straight from school pupil at university was given by Neville George. And in order to explain what that lecture was like, I need to go back a few hours to the first lecture I was given at Glasgow University. This was in the middle of the 1960s. So the first lecture I attended was natural philosophy, which was physics in those days. And it was at 9 o'clock on the first Monday morning, October morning of the term, 9 o'clock. And there'd be maybe around 300 of us packed into a lecture theatre with two great blackboards at the front here, revolving blackboards. And the lecturer basically filled with white chalk, formula after formula after formula. When he got to the bottom, he went to the second blackboard, started again with that, and an assistant, a janitor, I think it was, come in with a big duster. He paused for about 10 seconds and then started rubbing out the first one to clear it for when the second one was full, the third one would get filled with white chalk. And if you didn't move pretty fast, you weren't going to learn a lot. I actually thought that Robert Burns could have been sitting in that lecture theatre writing these lines from Tam O'Shanter at that time, the ones that go, like the snowfall in the river, a moment white, then gone forever. But then a couple of hours later, I was up to the geology department, which was, of course, up in the quadrangles in those days. And it was Neville George giving the first lecture in geology that I'd ever had. And what a knowledge dump that was in 55 minutes. Basically, actually, it's really worth quoting from this obituary here, just what things were like. This is particularly for younger members of the audience here. What was it like in those days? And this is a direct quote from the obituary written by Dr. McLean. And he says, a rowdy class of 300 first-year students in the post-war years could be a challenge. They were never rowdy for long, if at all, with Neville George. His charm and authority are still remembered by grey-haired men and women who can no longer recall precisely what a straight line is. Well, I qualify in both those counts pretty clearly. What he did was, came in and he had a box, not of white chalk, but full of coloured chalk. And he also had two big blackboards. And he proceeded in the course of 55 minutes to basically build freehand the map of the geology of Scotland using coloured chalk on one half and a whole series of cross sections, again, freehand on the other blackboard. And to me, it was a bit like one of these restaurant tasting menus that you read about these days with 12 courses, and every one that you get, you think, I wish I had a bit more of that. Well, Neville George's lecture was like one of these, except there were about 30 or 40 courses in it. And I still want more of them today. That's what he did to me. He absolutely lit me up. So that was Neville George. And that's why his medal is important. He was a really important guy. To the purpose of this evening, and Margaret asked me to read out the text of the citation in the scroll, which she'll present to Dr. Elsa Panciroli shortly. And this is the text. The Geological Society of Glasgow is honoured to award Dr. Elsa Panciroli the T.N. George Medal in recognition of excellence in paleontology for her outstanding contributions to the field and her transformative impact on our understanding of early mammalian evolution. Dr. Panciroli is a palaeobiologist whose research has significantly advanced our knowledge of mammalian origins, particularly during the Mesozoic era. Her work has focused on the Middle Jurassic fossil record of the British Isles, with a special emphasis on the Isle of Skye and the neighbouring Isle of Egg. Through meticulous fieldwork and innovative analytical techniques utilizing synchrotron tomography, digital visualization, she has described numerous new species and revealed critical insights into the anatomy, growth, and life history of early mammals and their relatives. Her leadership in the research project, The Birth of Mammals, Uncovering the Origins of Viviparity, exemplifies her commitment to exploring fundamental evolutionary questions. This work has shed light on the transition from egg-laying ancestors to live birth in mammals, a pivotal development in vertebrate history. Elsa's academic journey from her undergraduate studies in environmental science at the University of the Highlands and Islands to her PhD jointly awarded by the University of Edinburgh and National Museums of Scotland reflects her deep-rooted connection to Scotland's geological heritage. Her research fellowship at the Oxford University Museum of Natural History further cemented her reputation as a leading expert in paleontology. Beyond her scientific achievements, Elsa is a passionate science communicator. She has authored books, copies here, contributed to public science initiatives, and appeared on television, radio, and podcasts, making paleontology accessible and engaging to diverse audiences. Elsa was a contributor and appeared in the Hunterian Museum exhibition Women in the Rocks, and has just completed her term as chair of the Scottish Geology Trust. Dr. Elsa Panciroli embodies the spirit of the T.N. George Medal, excellence in research, dedication to public engagement, and a profound impact on the field of paleontology. Her work continues to inspire both the scientific community and the public, and is a most deserving recipient of the honour. Hand over to you, Margaret.
Thank you so much.
We have a copy of what he's just read in there. And this is the medal. Your name is round the outside. If you're trying to find it on the other side, I just let everybody see. It's a bit far to see it properly, but it's a lovely medal. And a pleasure.
Thank you so much.
Great pleasure to.
I'm really honoured. Thank you very much. I want to wear this around my neck like a 70s. I'll leave these with you if I can. Should I just start my talk? Yeah, so I'm recovering from a cold, so I might croak a little bit and cough now and then, but I am going to do my best. So thank you all so much for coming, first of all. It's lovely to see some familiar faces and some people I haven't met before. I thought I would talk a little bit about who I am and the work that I'm doing, and touch on some of the things that were mentioned in that lovely introduction as well. Yes, so I am currently based at Natural Museum Scotland as an independent research fellow, and I'll talk a bit about that project. Is this, oh, doesn't seem to be going. Oh, there we go. I'll talk a bit about that project that was mentioned there about the origin of birth in mammals at the end. But some of you might have seen at the, oh gosh, when was it now? The start of last year, I think it was, in March. There was a bit of a splash about this new dinosaur. So we're going to talk a little bit about dinosaurs as well, and some of the other animals that I've worked on before getting to the mammals. And part of the reason I want to talk about that is also because it contrasts literally in size. So this is one of the biggest things that my team and I have actually recovered, because I usually find things that look a little bit more like that. And that's the black bit on that rock is the fossil. Most of the stuff I work on is more like that size. So there's a real scale difference there. Now, my first excavation, I started young. As was in the introduction there, I grew up mainly on the west coast at West of Ross, and then a little bit on Loch Ness side. And apparently, I went back actually to West of Ross not that long ago to give a school talk. And this woman came up to me afterwards and said, "I remember you." I was like, oh God, oh no. She says, "I used to take you for walks when your mum was busy and you used to pick up sheep bones and tell me they were dinosaur bones." So obviously there was something there. And I have been doing, as was in that introduction, a lot of outreach work. I really enjoy talking with the public, and particularly with young people, but I also worked writing for The Guardian for a number of years about writing about all different things to do with the evolution of life on Earth and a little bit of geology and paleontology. I've also been a judge for the Hugh Miller Writing Competition. And one of the things I'm really passionate about is that kind of intersection between dry science, which we love, but also creativity and the kind of, you know, the other direction that you can come at these questions. So that's sort of one of my own personal interests as well. One of the reasons why I've written the books that I've written. So the sort of biggest one is The Beast Before Us, which came out in 2021. And it really grew out of my PhD work and my master's, where I began to learn about the origin of mammals. And it's that kind of feeling, I'm sure you've all felt it, where you learn stuff and you're just like, I can't believe it. That's amazing. I want to tell everyone. So I started writing them down and eventually realised that actually there's so many amazing things that a lot of people just don't get to hear about. And so I put them in this book. Then slightly later, I also published this one as well, slightly different tone for this book. It's much more of a sort of journey through geological time with lots of different animals, lots of different time periods, little vignettes, little bits and pieces you can dip in and out of. And also quite good because it's maybe for a wider readership. So that's some of the kind of the more public outreach side of things. But of course, one of the things that I'm here for is because of the work that I do on the scientific side. And this was me, one of the first years of my PhD with the team on the Isle of Skye, one of the two teams on the Isle of Skye. Some of you might recognise Steve Brusati in the middle there, who's a well-known paleontologist in Edinburgh, and you may know some of the other members of that team. So I've done some work with that group, but also, and in fact, before I move to the other group, one of the things that we found was that was mentioned again in that introduction. It was on the Isle of Eggs. So we did some field work there, and there's a really embarrassing story. I don't know why I told this to the press, and it ended up being the story that they ran with, obviously, literally ran with, which is I found the fossil I'm about to talk about, which is this one here, because I was jogging back to the rest of the team, having just wandered off along the shore, and I stepped on it. And I kind of took another few steps and did that thing where you're like, hang on a minute, and you walk back and realised that it was potentially a dinosaur bone. But this turned into news stories about how I was apparently a jogger. And I was jogging on the beach. I just got this, they were painting this image like I'm some kind of, outdoorsy jogger in my lycra or whatever. But no, it was on fieldwork. And it did turn out to be from a stegosaur. It's actually one of the hind limb bones, the lower hind limb bone. Quite fragmentary, and a lot of stuff that we do have from dinosaurs in Scotland is quite fragmentary. We don't have a lot of very complete fossils. And that's going to be in contrast with some of the things I'm going to show you in a little while, some of the little things which are exceptionally complete and which is what makes them really unique. So this is the other team that I work with on Skye. And this is a mixed bag of us. There's Stig and myself from National Museum Scotland framing the outside of that group. And then on the inside, Richard Butler from the University of Birmingham and Roger Benson, who's now at the American Museum of Natural History. And we do most of our work near, well, I'm sure a lot of you know exactly where this is. This is near Elgol in the south of the Isle of Skye. And this is where we're finding mammals. We haven't found them anywhere else on the island yet. And it's a particularly exceptional site with a really interesting history. So there's the team there, and a couple of people also associated with this work are Nick Fraser and Professor Jishi Luo. This is what the rocks look like on a particularly beautiful day. I was very much misled early in working there because the first about 4 years that we worked there, the weather was like this. And I was like, wow, I don't know what everyone's complaining about. This is amazing. And then ever since, we have not had a single year like this. So the last 5-6 years have been horrendous. So it just goes to show its luck. But the rocks are beautiful. This really lovely limestone, absolutely gorgeous to look at and gorgeous to work with. Cut through with dikes. This is actually a dike that's just created this little cliff here. And that's me and Stig taking a look at one of the fossils. So it's a really fantastic place to work. A little bit of the geology there and the location. You obviously all know where the Isle of Skye is, so I don't really need to tell you there, but it's down in the south of the island at Elgol. And it's part of the Great Estuarine group that we work in, the Kilmalooeg Formation, which is one of the youngest in that group. So most of the material that you hear about on Skye comes from the slightly older Duntulm, Valtos, Lealt. So it's quite different both in age, but also in the actual content and the environment it represents. So this site in Elgol was found in the 70s by, people usually credit it to Bob Savage, but it was actually Mike Waldman up there who sadly just passed away at the end of last year. He found it when he was taking a group of, what's it called again, the medal? Duke of Edinburgh, a Duke of Edinburgh group from the school that he worked in. He was a paleontologist but had become a school teacher. And he, you know what it's like being a geologist or a paleontologist. Wherever you go, you want to look at rocks. So he dragged them along the shore to look for rocks and fossils and ended up finding this exceptional new vertebrate fossil site. And he worked it with Professor Robert Savage for a number of years in the 70s and 80s. And then there was a hiatus before our work began. And this is what the rock looks like close up. It used to be called the Ostracod limestone. I think you can see why. There are just millions of them dotted through, and lots of viviparous, lots of other concostricans and ostracods all the way through this. And it really betrays the fact that this is a very freshwater, perhaps exclusively freshwater environment. There doesn't seem to be any sort of saline input, no brackish water. So that makes it quite unique, actually, among the Great Estuarine group, because a lot of the other ones are sort of near shore environments. And it also affects what we find in it in terms of the vertebrate fossils. So I mentioned this, this is what we call the Elgol dinosaur. It is, at the moment, Scotland's most complete dinosaur, but you'll be struggling to identify any of the bits because it is in pieces. It's battered up and fragmented. I don't know what I'm pointing at in the middle there, but we think it's part of the hip, but it's very difficult to tell. So maybe not the most impressive thing, but as I say, technically the most complete. And it was found by the team. This is the year we found it. You can see all the men have to stand around and take a very, very good look, scratching their chins. And I just went off and took a photo and I thought it looked quite funny. But it's actually on this little bit of rock here where Richard is just taking a look. And he found it when he was clambering up amongst these boulders. And this is what it looked like in the field. So we really weren't sure what we had, how much of it would be inside the rock. But we decided, really from having a look at it, that it was actually just going to be too difficult to collect. And so the decision was made that we wouldn't take it. Because in our work on the shore, we've got, of course, a few things to balance. One is we want to make sure we don't have too much of an impact. So we don't collect things unless we're certain they're going to be important. But the other thing is logistics. I mean, you saw that was on top of a boulder, on top of boulders on a tidal shoreline. And when the tide comes in, it comes to the base of those rocks. So I mean, how on earth could we possibly get this thing out? So we were like, yeah, let's not collect it. We're going to leave it. I could not stop thinking about it. I mean, I think maybe it's different for the other guys in the team, but growing up in Scotland, I was thinking, God, when I was a kid, if somebody had told me there was a dinosaur on the beach and that some scientists saw it and didn't collect it, I would just think that they were just pure evil. How could they not collect a dinosaur from the shore? So I kept thinking about it. And what really made me, in the end, push the team to collect it was I was looking through Bob Savage's diaries from his fieldwork in the 70s and 80s, and I found this sketch and realised, it's maybe not that obvious to see, but I realised that this is actually the same fossil. And he had a little note in his diary, like, ? Dinosaur? And they obviously decided not to collect it either. I was like, how long is this thing going to be? 166 million years it sits there. And now nobody wants to collect it. So anyway, I managed to persuade the team. It was logistically, it was very, very difficult. But we got a couple of big lads in from Canada, from Research Casting International. And we managed, they knew the techniques for how to get something big like this out. And we managed to get it down. We actually scavenged all of this stuff from the shore and used it to basically lower this, not the ropes, sorry, we brought the ropes. We used it to lower this specimen down onto the rocks. We tied it all up with ratchet straps, and then what the locals lent us a boat and a dinghy. We managed to get it back to the shore and take it away to study. So it was a great fun to collect. I think it was worth it. I don't know if they do. They did most of the heavy lifting. It was very, very big and very difficult. But we got this beautiful reconstruction done of the kind of animal it belonged to. So this is one of the relatives of things like iguanodon, that group of dinosaurs. And obviously we only have bits and pieces of it, but you can kind of imagine we're going for a sort of misty isle. You can imagine this is Skye, wandering around with lots of companions. And I'll draw your attention to some of them in the trees, for example, like the little mammals I'll be talking about in a moment. I like this photo because I like to embarrass Roger, but this is how we spend most of our time looking for fossils. They're not dinosaur size, they're tiny. And we're bent over on the shore, just usually with hand lenses, trying to find little clues that tell us that something exceptionally small but really important might be in those rocks. And the other thing about this is it shows you that where we search is at the very, very, very lowest tide line. You can see the kelp beds are exposed. So we time our fieldwork for that low, high and low spring tides in the spring. There's the other Roger who joined us one of the years, also looking, you can see he's demonstrating excellent technique with his hand lens there. And what he's looking at, well, these are really, really obvious and very beautiful versions of what we're looking for. Little clusters of bones or jaws that belong, all of these bones belong to just one animal. So it's a near complete skeleton. So these are particularly good looking ones. That's a mammal jaw at the top. I think this one was actually a little salamander rather than a mammal. But most of them don't look like that. And I think I've got some ugly ones to show you after. Most of them are much more difficult to recognize. So we cut them out. We, of course, have to get permits from Nature Scott. This is a protected area. And we also only cut outside of bird breeding season because this is a protected area for golden eagles as well. But we minimize the damage that we do, and we also try to then afterwards disguise where we've cut because we don't want it to be too obvious. And I think looking at the way that our cuts are weathering, within 10 to 20 years, you can't tell that anybody cut anything, which is exactly what we want. We want it to be invisible to future generations. So a couple of the things that we found, I thought I'd show you some of the non-mammals first before we get to the really interesting ones. This one is the one I showed you at the start. This is actually not a mammal. This one that's what you can see here, is this bit here. And you can see that when we scanned it using a micro CT scanner, it turned out that nearly the entire skeleton was disappearing into the rock. This is exactly what we want. We're looking for something that is just beginning to erode, and hopefully we've still got the rest of the skeleton. Sometimes we scan it and the whole skeleton's already eroded and we've only got the last bit left. So it's pot luck. This turned out to be a lovely little lizard, a squamate. And the reason that this, and actually all of the fossils we're finding, are really scientifically important is that they are lying in the Middle Jurassic at a time when all of the groups that are alive today, including lizards, but also mammals, in a way dinosaurs too, because birds, are all diversifying. They're all being basically kind of set up. All of the traits that make them what they are originate around about this time. So any fossil we find helps us tell that story, helps us understand how their bodies are assembled and what it was that perhaps led to their later success. This is another one that I particularly like to show because of the way that it's been found. You can see here the different pieces. This one is actually a composite. It's one skeleton, but it's a composite in the sense that the first bit was found by Waldman when he first went there in 1971. He collected it and he obviously thought he got the whole thing. And then we saw in 2016 some bones sticking out, collected those. And I do not know how Roger noticed, but he somehow noticed that they belonged to the same specimen. And so we ended up with this, this complete skeleton, or near complete skeleton, that turned out in this case to belong to a salamander. And we're looking at a similar story, but for the salamander tree. This is something really early in their history, and what we can find out from the skull and from the rest of the skeleton tells us about how their bodies were assembled and why they're so successful today. And if you're interested in knowing more about the general fauna that's found there, there's this wonderful, well, I say it's wonderful, I shouldn't say that's my own paper. I only did part of it, obviously, but it's a good sort of summary, is what I'm trying to say, of the stuff that we've found, but also how it compares with contemporaneous sites around the world. So I recommend checking that out. There's a few interesting things I won't talk about in this talk, like the turtle here, and a few bits of dinosaur as well down there, including teeth. So this is the kind of ecosystem that you can imagine that these represent. Something freshwater. So we've got, obviously this is a watery environment, but these creatures are living around and within this water, potentially falling in, some of them we think out of trees, into the water. But we don't actually entirely understand why they are so well preserved, why we're getting these whole skeletons preserved in 3 dimensions, that is not not compressed flat into a layer. That's something that we are actually putting together a Leverhulme proposal right now to understand the taphonomy of the site. Why are they all here? So I can come back and give you another talk about that when we have some answers. But what I'm going to move on to now is the bit that I'm most interested in, which is these little dudes in the corner, our little mammals, our ancient, I won't say ancestors, but cousins that lived at the time of dinosaurs. So I began my work in this area working on these two blocks, which were just sort of colloquially known as Block A and Block B. But they were the missing mammal blocks because they were actually found, again, by Bob Savage and Mike Waldman back in the 70s, and then they were misplaced. And this happens in museums, you know, things get moved around. Sometimes they go in a box and then nobody can remember where the box went. It shouldn't happen, but it does happen. We're all human. And there was a real push to find them again, because as people like Professor Susan Evans said to the then keeper of the collections, you know, they recognised straight away were some of the most important fossils that had come out of the site, partly because they're so complete, but especially because they're mammals. And in the 70s, we still really didn't have that many complete mammal fossils in the world. So there was a push to find them, and they were eventually relocated. Nick and Stig found them, and they then wanted to find somebody to study them. And luckily, that was me. I was very, very delighted to be able to come and work on them in my PhD. Now, I was going to be working on both of them, but I ended up focusing first on this block, which became known as Block A. And the first challenge that I faced is, you'll notice a lot of the images I've shown you of these fossils they're coming from CT scans, micro CT scans. But when we tried to scan these blocks, you could see the sort of size of them there. You know, they're relatively large for a micro CT scanner. And so when I got my data back, in those three boxes, each one of those is a cross-section through the fossil, which is here. And you can see in this image here I've highlighted, that's what the bones look like. I mean, that's rubbish. That's really rubbish data. If I tried to reconstruct the skeleton, I would basically not be able to tell you anything. It'd be blobs, all blobs. And I scanned it in 3 different places, and then I spoke to the guys that build the scanners, and I said, can you do this? And they're like, oh yeah, bring it down to our headquarters, we'll do it for you. They couldn't do it either. It turned out to be nearly impossible, and the reason being that you can't get the X-rays to penetrate so deep into this particular material. It's really not X-ray friendly, let's say. So it was a real challenge, and we ended up taking it to the European Synchrotron in Grenoble in France. This was my first encounter with Synchrotron. It's ended up being a kind of cornerstone of all my research now. And it's an incredible place. For those who aren't familiar with this, what you're looking at here, this big donut, essentially what they do is they have this sort of starter gun in the center that fires electrons that go into this ring, and they're going around at like ridiculous speeds. And as they go around, they're bent off with magnets, which produces X-rays. And those X-rays are far, far more powerful than anything you can get in a micro CT scanner. They're so powerful that you can see things down to sub-micron level. So, you know, a thousandth in the plural of a millimeter, really, really tiny detail, sort of microstructure of bones. You can virtually see atoms of these things, not quite, but it's very, very powerful. And the great thing about it is that you competitively bid to get time on it. And if you get the time, they pay for everything. They pay for your travel, they feed you, which before lockdown was brilliant because it was all fabulous French food, but gone down a little bit since after lockdown. But basically you get a kind of holiday, but a science holiday, where you spend day and night in a windowless room firing X-rays at fossils. But if you like that kind of thing, and I do, it's really good fun. So this is Vincent, who is one of the world's leading experts in synchrotron tomography. You will see, when you start looking, you'll see his name on every paper that's got to do with this technique. He's brilliant at it. And he has, using the extremely high-tech sticky tape, stuck one of the fossils in front of the beam line there. Obviously, it's not turned on right now. And then when it came out, that's the kind of image that we were getting. So you can contrast that with the really rubbish one I showed you earlier. This is exceptional. And it was only by doing this that we could study these fossils. So these were the first ones from this site in the Isle of Skye that were ever imaged by synchrotron tomography. And we realized immediately that this was the way forward. And this is how all of them are now studied if they can't be X-rayed, micro-CT scanned. So that was the fossil there that I showed you, block A, the mysterious missing block, and it turned out to belong to this little animal, Borealestes serendipitous, which was quite cool because that was the first mammal found by Waldman and Savage, well, by Waldman actually, and then he brought it and showed it to Savage on the very first day that he went to look at the site. That's what he found with the kids sticking out of the rock. And it was the first one that had been found of this particular taxon, so he named it Borealestes, the northern rogue, serendipitous, found by luck. Although he always said to me, it wasn't luck. I did my research. I knew they were going to be there because he had looked up Peach's old memoir and he knew that there was a real good chance there'd be fossils. But still, a beautiful name, Little Northern Rogue. And in 2016 or 17, I forget now, we ended up finding a second species of this same genus. And so my work then revolved around basically describing these. You can see the skeleton scattered through the rock there, but there's some jaws up in the top and some limb bones. In these, the bits that are highlighted, that's the bits that we have of the skeleton. So until recently, these were the most complete mammal fossils from the Jurassic to come out of Scotland. And this beautiful reconstruction was done by Matt Humpage at Northern Rogue Studios. I wonder where he got the name of our little Northern Rogues. So more recently, I then moved on to Block B. And Block B was even more exceptional. You can see already just looking at it, all that black stuff, that is an entire skeleton. So we already knew this was going to be cool. What we didn't know is just how cool. Because trying to study it like this, even though it's at the surface, we would never have been able to get the kind of detail that I'm about to show you from synchrotron tomography. But let's take a little detour first and come back to that, because I think we need to understand a little bit more about why these specimens, I keep saying they're so important, so amazing. Why are they so important and amazing? Well, obviously, mammals, the group we belong to, are, well, they're considered to be the kind of dominant, although I don't like using that word, the most diverse taxonomically and ecologically, body size of all of the vertebrate animals on the planet today. Everything from tiny, tiny little bumblebee bats right the way up to blue whales. I mean, really incredibly successful, and all that variation has happened relatively fast. You're geologists, so I can say relatively fast, about 60 million years, because that's, we all know that's not very long. But the things that make them really unique and interesting are things like being, having fur, producing milk, and particularly also things like how they grow and develop. So we've got the three main kind of modes of life that we see among them today. There's a couple of them that still lay eggs. All their ancestors used to lay eggs. But most mammals, as we know, give birth to live young, either like placental mammals, like us, give birth to quite well-developed young, whereas the marsupials give birth to very underdeveloped young that spend a long time suckling them with milk. And these groups today are what we would call the crown group. This is the modern group. But obviously my interests lie much, much earlier in this tree. One of my big research questions, and the one I work with my colleagues as well, is about growth. Because mammals today have a particularly distinct growth pattern. They grow up really quickly. We don't, because we're weird. But most mammals, especially things like mice and stuff, you know, they grow really, really rapidly to adult size. But most of us don't get any bigger once we reach adult size. I don't know, I feel like I'm growing all the time. I just seem to get bigger every week, but most of us stay the same size. And that's the mammal pattern. Fast, rapid growth, and then you stay the same size when you're an adult. But if you're a crocodile, you just keep getting bigger. And the question is, when did this mammal style of growth emerge? Were there ancestors like that too, or were they more like crocodiles? And actually nobody until recently had any idea. I couldn't answer that question. So my research group at the moment, we are really fascinated with questions like this. When did the traits like this actually emerge? So that's, yeah, so that's what it would be called. Determinate truncated growth is what we call that, that pattern. So the crown group are around today, but I'm interested in these little guys here, and there's lots of questions still to answer about them, but we are beginning to answer them. So one of my close working colleagues, Dr. Ellis Newham, he's been getting at this answer using synchrotron again, but this time looking at growth rings in teeth. So there's this material that grows around your teeth called cementum. This is it here. And it grows in all of our teeth as mammals, in fact, even non-mammals. And it's laid down in annual rings, light and dark rings, just like growth rings in a tree. So you can essentially cut this tooth and just count the rings, and you'll know how old that animal was when it died. So this has been used by ecologists for quite a long time to study things like caribou population dynamics, things like that. And the stroke of genius was to realize that you could apply this to the fossil record. And the only way you can really do that is using synchrotron because it's non-destructive. And you can't cut one of these teeth because they're so rare, but you can blast it with X-rays and it's none the worse for wear. So his research was really interesting because he looked at longevity in these tiny little mammals right at the base of the mammal tree, living alongside the dinosaurs and before them in the Triassic. And he began to get tooth counts that are massively not what you would expect for such a tiny animal. So all these animals in the Triassic and Jurassic are pretty small. Most of them are little tiny mice, maybe even smaller little bumblebee bat-sized things. And yet some of their teeth, he got counts of up to 14 years. I don't know how many of you might have had a pet rat or a mouse, but you're lucky if they live more than a couple of years. That's really strange for such a tiny animal to live so long. Oh, yeah, I should have shown that while I was talking. So for example, this little shrew here lives often less than a year. And it's a similar kind of size to something like Morgan-Eucodon, which is one of the animals that you see here that lived for 14 years. So what that tells us is, first of all, wow, they lived so long, but they must have grown differently and had different life history patterns. Because if you're living so long, you're not going to grow really rapidly, do everything at the start, and then just spend the next 13 years going, well, what am I going to do now? Just keep having babies, you know, like they must have done something different. So it gave us more questions to answer. So this was basically kind of what we were wondering is, were they growing perhaps more like crocodiles? Were they living this long, but actually taking a lot longer to get to maturity? That was the big question. And so the reason I've told you all this is because we're then going to look back, because the fossils from the Isle of Skye have helped us begin to answer this question, and are continuing to help us answer this question. And answer questions like, were they born precocious, so that's like placental mammals, really well developed, or altrical, really undeveloped, like a marsupial? When did they wean? Because growing in your adult teeth and weaning, that's a really key developmental stage for mammals. And we also, of course, wanted to look at other kind of developmental markers in their growth. And the group that these fossils that I'm talking about belong to are the docodontans, which are right down here at the very base of the tree. So whatever we find in them is likely to be representative of the early growth of most mammals. Hey, my throat's doing quite well, actually. I'm quite impressed. So docodontans, I want to enthuse about them for a moment because they are fabulous little creatures. Here's an artist's impression of some of the earliest docodontans, which my student Sofia Patrocínio from the University of Lisbon in Portugal recently described. This is the fossil of this little animal called Geological. And it turned out that this is one of the oldest docodontans. It comes from the very latest Triassic to the earliest Jurassic, from Greenland, of all places. So they have a very, very long evolutionary history, and they're a really interesting group for a number of reasons. Actually, you can maybe see it in this picture here. One of the things is that their teeth are actually quite complex. In other words, they have lots of different cusps. And most other early mammals at this time just kind of have maybe 3 big cusps in a row, and that's it. Very simple teeth. So their teeth were more complicated. And that is tied, of course, to what they could eat. They could process lots more different kinds of foods, and therefore ecologically could do a lot more different things. So we find this group, they're some of the earliest mole-like animals, some of the earliest otter-like animals. They're beginning to diversify. And this is long before our ancestors, our true mammals, later on in the Middle Jurassic and beyond. So back to this fossil from Skye. What was it? Well, first of all, we have this fantastic one here, but then in 2017, you'll notice this story keeps happening with all the ones we're talking about. We found a second one of the same taxon, which is great because we could study them together. But when we looked at this new one, it turned out to be even better than that, because it turned out what we had was an adult and a juvenile of the same mammal, an animal called Chrysatodon. And this comes back to answering these questions about growth. Baby mammals from the Mesozoic are, well, I don't think there's any other skeletons in the world of Mesozoic mammals from this time period. We've got some teeth, a couple of jaws, but this is one of the first. So this was going to let us answer some of those questions about growth and development. So this is the baby one. I'm going to concentrate on that first. Some of you, if you ever saw me giving talks when I first started my PhD, I had done this reconstruction, or I was trying to do this reconstruction. I used to call it the smoosh, and you think you can see why, because this fossil, it is, there's a partial skeleton in there, but the whole thing is really, really crushed up. You can sort of see those big pink, I've done them in pink. Obviously, they're not naturally pink. I've done them in pink, the jaws there with the teeth, but there's a skull on the other side of that all crushed in, and there's bits and pieces of limb bones. But it's really, really crushed up. So it was a real challenge in the first instance just to reconstruct it. But when I did, I found that just putting aside the rest of the skeleton, this was what we had of the skull. So that's quite a lot of skull material. Even if it is crushed up, you could still tell an awful lot from it. So what I then did was work with a 3D artist who reconstructed that as a beautiful polished skull. And one of the things we realized from the synchrotron data was that not only did it have this lovely array of little bitey teeth, but can you see these green teeth here? You can guess what those are. Those are actually the baby teeth. Sorry, the adult teeth. The teeth that are in the jaw are its baby teeth. This animal hadn't finished weaning yet. All of its adult teeth were still yet to push up and emerge. In other words, we had a really, really young animal developmentally. If you want to see what that looks like in us and dogs, look away if you're squeamish. This is a similar kind of thing. Our teeth actually sit up inside our jaws as babies, and thankfully are invisible because it's horrifying. And then they push all of the baby teeth out and replace them. So what we essentially had is, I'm a bit like the dog there. That is essentially what you're seeing in that image. Those are those adult teeth inside the jaw ready to push the baby teeth out. So this meant we could start to think about things like weaning and growth rates and timing of development. So one of the first things I realized is that the percentage of teeth that had already erupted told us something about developmentally, how far along this animal was. It wasn't a baby. It was a juvenile, what we would say. So technically it's not adult yet, but it's not really, really young either. In fact, that it's kind of good because, as I say, it's at this key stage. We also compared that with a data set of the mammals that are alive today. We looked at when they weaned based on how many of their teeth had been replaced. And based on that data set, we could say that this fossil mammal was very likely, if it followed the pattern of modern mammals, very likely to either be weaning or have weaned. So it's at this key moment in its development. We could confirm that by comparing it to this data set. So I mentioned cementum and how you can count it to see how old an animal is. So the next question was, okay, it's weaning. How old is it? If it lives to something like 8 or 14 years old, when is it doing this? When is it pushing all of its baby teeth out? So we went to the synchrotron and we synchrotroned the teeth, and we counted the rings. And what we found is that the most we could find in terms of these increments was 2. So 2 years old, that this little tiny thing the size of a shrew had only just started replacing its teeth. So we had to put an error bar on it. It could be maybe as little as 7 months. I think it's far more likely, though, with 2 increments like that, to be closer to 2 years. And the reason there's that error bar is just because those lines of cementum, depending on what season an animal's born, can tell you a number that's slightly too high or slightly too low. So a 2-year-old, teeny weeny little animal just replacing its teeth, just weaning. When we compared that to a data set of all of the mammals that we could get the information for, it was, I think, 278 or something like that we had all in total, of placentals, of marsupials, and of monotremes. Well, all you need to take home from this graph when we plotted it all together is that even with the massive error bar, this animal falls way outside the range of what you would expect for the age of a tiny little creature to be when it's replacing its teeth and weaning. So what does that mean? It means it developed really, really slowly. So it took 2 whole years. So a mouse, for example, would go through the same process in weeks. This thing's 2 years old before it does it. So they must have been growing really slowly, like we suspected, a lot more like a crocodile, although not, of course, exactly the same, than like mammals are today. So that's one of the big take-home messages. We had that published in Nature because it really is quite an important piece of this story. But again, of course, all it did was open doors to 100 more questions that we want to ask about mammals. And this is the image that I opened with, was Maya's beautiful reconstruction of the adult and the juvenile, perhaps with a future dinosaur to be discovered in the background there on the Isle of Skye. So I'll finish up by just touching on my current research, which is, as we mentioned earlier, to do with the origin of live birth. So I mentioned that mammals all come from ancestors that laid eggs. So I'm just showing the very tip of the mammal tree here, but actually, as you'll find out in my book, Beasts Before Us, the tree goes way, way, way back. We split with reptiles like over 300 million years ago. And all of those ancestors of ours, egg layer, egg layer, egg layer, egg layer, all the way up, we think, right up until when? Well, we don't know. We know that monotremes, that's the platypuses and the echidnas, they still lay eggs. So we assume that live birth must have emerged somewhere between where they split and where the modern mammals emerged. But that's not necessarily even the case, because when you look at things like lizards, lizards have got something ludicrous like 200 separate events of evolving live birth. I don't know if you know, lizards give birth to live young, some of them. And it's happened over 200 different times. Maybe that's what it looks like. Maybe lots of different mammal groups became live birth givers, and other ones remained egg layers like the monotremes. We actually have absolutely and utterly no idea. And if anybody ever tells you they know, they're wrong. We don't know. We can guess, but we really don't know. So that's what we want to find out. What I want to find out in the next, how long have I got? 4 years, I think, of my research fellowship. And the way that I'm going to try and do it with my colleague Luke Weaver and also Ellis, who I mentioned earlier, is by looking actually at their bones and the microstructure of their bones. Now, Luke, he did this totally amazing paper that blew my mind in 2022, where he started looking at, this is the histology, is what they call the study of the microstructure of bones. What his study showed was he literally cut, he didn't use synchrotron like I do, he literally cut a whole bunch of bones up and looked at the patterns of growth. And what he found is that if you are a marsupial, you give birth to really, really underdeveloped young, they have to grow quite a lot to become adults. And this pattern is recorded in the way that they lay the tissues down in their bones. And the pattern summarized looks like that, right? You don't need to worry about what the different fabrics are. but that's the pattern. Placental mammals, they're quite big when they're born compared to marsupials. So they don't replace as much of their bone, and they end up with what he calls a sandwich pattern instead. And he found that you could actually just tell if an animal was one or the other just by looking at their limb bones. And he then looked at the fossil record for a particular group of mammals from the late Cretaceous, and he found that they were more like this than that, and was able to say they were placental-like in the way that they grew. So this is a real game changer. And of course, the moment as I reviewed his paper, and you're not allowed to email people when you're reviewing their paper, but as soon as I read it, I'm like, I want to talk to this guy. So I reviewed his paper, and as soon as the process was over, I emailed and I was like, I love your paper. I want to use this for Mesozoic mammals. Will you join me? I've got Jurassic mammals from Skye. Let's start looking at their bones. And he was right on board. He is very, very enthusiastic American. So this is what we're doing now. Over the next few years, we have been scanning every single bone that we can get our hands on from the fossil record, particularly of the Jurassic, all the way through to the Cretaceous. And we want to try and see if we can establish a pattern for egg layers so that we can then look at the fossil record and say, egg layer, egg layer, egg layer, live birth. And that's where it is. That's where it happened. Or that's where it happened, and that's where it happened, and that's where it happened. Whatever the pattern is, this is the method that we're going to use to try and answer that. It might not work, but hopefully I can come back maybe in a few years and show you the results that we have of this study. And if we can pinpoint it like that, it will have a huge set of implications for understanding everything that we know about mammals and how they've evolved and how they've achieved the kind of success and diversity that we see today. A few little fun stills from the ongoing work. This is how we actually do it. We mount these bones. This is actually a echidna's bone on a piece of kind of weird gummy stuff that doesn't stick to the bone when you take it off again. We get our results. These are the cross sections from the synchrotron. We've got hundreds of them on little mounted things up in the top there. And we are just scanning the world. We're scanning everything we can get. And it's a work in progress. So I'd love to come back and tell you more about that in a few years' time. But with that, I'm so pleased that my voice held, because I really didn't think I'd be able to talk for this long. I want to thank all my co-authors and collaborators, but also thank you all so much for having me here, and thank you so much for this award. It really means an enormous amount to me. It's the first thing like this that I've won, so thank you.